Alrighty. Okay. So it's gonna be a hard one today. I looked at the description. I don't like palindromes all that much for coding problems, but put down a disclaimer just in case anyone watches and gets bored. Alright, you're given two integers n and k, an integer x called k palindronic. If x is a palindrome, an integer x is called k palindronic if it's a palindrome and divisible by k. An integer is called good if its digits can be rearranged to form a k palindronic integer. For example, if k is 2, so it means it has to be a number that's a palindrome divisible by 2. 2020 can be arranged as a k palindronic integer, whereas 1010 cannot, because you would need to have the 1 in the last spot, and that wouldn't be divisible by 2. So anyways, 2002 would be a k palindronic integer, or would be called a good integer, as well as 2020 is a good integer. Return the count of good integers containing n digits. Note that any integer must not have leading zeros neither before nor after the rearrangement. For example, 1010 cannot be arranged to 101. Okay. So if n is 3 and k is 5, there's 27 good integers that are 3 digits indivisible by 5. Some of them are 551 because you can range that to 515, 525, 255, 552. If n is 1, it's 1 digit, and k is 4, it's just divisible by 4. It would just be 4 and 8 as things that are satisfying that. And then for 5 digits divisible by 6, there's 24,000 or 25,468. So I think I'm gonna. So the numbers that are the number digits would be 1 through 10. So that's like 1 through a million, and it has to be divisible between 1 through 9. So I think what I'm going to do is I'm going to try to work on, since I really don't know what the best way to do this, I generally try to start by doing the simple cases or simpler cases, and then work to expand it to generalize it to more cases, hopefully to all cases. So let's consider let's say k equals 1, so divisible by 1. So basically any number that can be arranged to palindrome, and go through all the n's, or as much as the n's until we can generalize. So if we're dealing with 1 and it's 1 digit, then it would just be 1 through 9. So there's 9 numbers. If n is 2 digits divisible by 1, not starting with 0, it'd be like 11, 22, 33, up to 99, so that should be 9 numbers. If n is 3, we're dealing with 1 as the start, some number, and 1, or 2 as the start, some number, 3, some number 2, 3, some number 3, all the way up to 9, some number 9. And since x can be 0 through 9, that should mean that there's 9 times 10 ways to do that. So that's 90. I'm going to test that. So let's go ahead and create n is 3 digits, k is 1. Returns. Well, that wasn't right. Okay, so if you have 3 digits, so 1 1 1 1 2 1 1 3 1 1 4 1 1 5 1. Oh, it needs to be rearranged, right? So technically it could be like, since 1 0 1 works, it could rearrange to like 1 1 0. Technically you could rearrange it to 0 1 1 if you're just considering the digits. But then 0 can't be the leading one. So how to do the rearrangement question? So there's 90 combinations of the first 2 digits, and then how many combinations of the rearrangements? Ninety combinations of the first 2 digits. I wonder if you can do, I wonder if you can just do, it doesn't have to be, so the palindrome is 1x1 or 2x1, but we just need to know how to rearrange it where you have a pair of numbers that are 1 through 9. I guess it'd be called permutation. Permutation of a pair 1 through 9, like 1 1 2 2 3 3, plus a singleton 0 through 9. Then these are overlapping cases as well. Because if you have a pair of 1s and you have a singleton of 1, then kind of overlap cases, they're not disjoint. So how to do that? Permutation of a pair of 1 through 9. So it ended up being 243, which is, I want to say 11. 243 is divisible by 11, I'm almost sure of it. Nah. Why did I think it was divisible by 11? 1, 1, 3, 2. I think if the first and last digits add up to the middle digit, it becomes divisible by 11. 253 is divisible by 11. Okay. Alright, 243 is not. 243 number of ways to have 3-digit number divisible by 1. 3-digit number that has 2 of the same digits and 1 other digit. 2 of the same digits and 1 other digit. Huh. So So it could be 111, 222, 333. Those are all the same digits. So that gives you 9. And then if you just talk about the ones where it's 2 of one digit and 1 of something different. 1 of something different. So do 1 through 9. 1 is something digit, so it could be 0. So 1, 1, 1, 1, 3 of so if you had so if you have a 1, so let's consider the case where one of the digits is 1, like the first digit is 1. Because I think if the first digit's 1, I can probably generalize it to the first digit being any number. So what is 243 minus 9? And I think that's divisible by 9 as well. 234 divisible by 9. 26. So I think like if you have a 1 something, there's basically 26 ways of doing that somehow. Because you're excluding the ways that it's not all identical. I guess if you include the ways that they're all identical, it would be 27. So 26 ways. So if you start with the 1, then it's like 1, and then like something besides 1. So 2 through, it could be 1, 1, and 2 through, or 0 through 9 excluding 1, anything besides 1. So that's 9 ways there. Here, this is, let's say, not 1. One, 1, not 1. There's 9 ways of doing that, right? And then it could be 1, not 1, 1. And then there's another 9 ways of doing that. One, 0, 1, 1, 2, 1, 1, 3, 1. There's 9 ways, 9 ways. And that adds up to 9 and 9. Where does the other one come from? So if you have a 1 to start, you have to have a 1 also in a 3-digit number. So it could be 1, not 1, not 1 that matches. And there's 9 ways of doing that, maybe? Yeah, like 1, 0, 0, 1, 2, 2, 1, 3, 3, 1, 4, 4. Okay. this is like 1, 0, 1, 1, 2, 1, 1, 3, 1. And this one's like 1, 1, 0, 1, 1, 2, 1, 1, 3. So that ends up being 27 total ways times 9, which is 243. Yeah. Alright, so there's that. So if you have n is 1 and k is 1 is 9, n is 2 and k is 1 is still 9, n is 3 and k is 1 is 243. Well, that's actually 9 cubed, right? 27 is, no, 9, 27 is just like 3 to the 5th power. 27 is 3 cubed, 9 is 3 squared. I wonder if that has any bearing on things. 9 is 3 squared. Alright, let's go ahead and just see what happens if you have n is 4. N is 4 and k is 1. $252. Alright, so n is 4, total is 252. So how does that work? We have so this one I can ignore. Well, how did this work actually? What about the 111? Like, why didn't this thing come up to be? So this ended up to be 27 ways of creating something that starts with 1, but doesn't include 111, 222. So if it doesn't include 111, then why does it still multiply by 9? One one zero, 111, 110, 112. There's 9 ways of doing that. And there's 9 ways of doing this. And there's 9 ways of doing this. And they're all disjoint. They're not overlapping. So there's 27 ways of doing that. Starting with 1, it's a good number. That doesn't include 111. So shouldn't this be 28 ways rather than 27 ways? Unless I'm double counting something. Don't see how it can possibly be double counting here. It has to start with a 1. And the other one, oh, it's 100. So 100 doesn't actually work. You can't rearrange 100. So you could rearrange 122, but if you try to rearrange 100, it becomes 010. So not 1 0 0. Okay, so it's actually here that's 1 1 1, 1 2 2, 1 3 3. Those are all palindromes, or those are all good. And because it's not 100 there, then it's still 9 possibilities. Okay, so okay. So it's actually not 1, not 1, not 1, but 1 plus a pair. Okay. So if n is 4, then we're dealing with starting with a 1 through 9. And so this doesn't actually increase it that much over n is 3. So it could be 1, 1, gosh, 1, 1xx, 1xx1, or 1x, 1x, or 1xx1, where the x is the other digit. Alright, so let's go ahead and consider those. So if it's a 1, 1, and you have a pair, that could be, is that 9 ways? So this could be, can't be double zeros, or can double zeros? I think the double zero case is always going to be rough. So like 1 1 0 0. There are ways, no, that works, because you can rearrange it to be 1 0 0. So that should equal 9. Well, the pair can't be well, let's exclude the excluding pair of ones. So that should be 9. So there should be like 1 1 1 0, 1 1 2 2, 1 1 3. And then you have, again, not including all ones, 1 1, or 1x, 1x. This could be any number. So there could be 9 ways of doing that. Again, not including zeros, not including all ones. Or I guess excluding. And then lastly, it'd be 1xx1. There's 9 ways of doing that, excluding all ones. So that gives you a total of 27, where you start with 1, and then you multiply by 9, that gives you 243. So there's 243 times 9, and the ways of doing that. And then how do you tab in the, well, you can't just tab in all ones. Well, yeah, you can actually. So there's 27 ways of doing above, plus one way of one 27 above plus all ones, so that's 28, and then 28 times 9 is 252. Okay. All right. I'll keep on doing this until I actually see a pattern. Test case 5. And then after I see the pattern, I have to generalize it even further for all divisions, all possible divisions, divisibility. All right, so actually let's do test case. Let's do them all. So 6, 7, 8, 9. I can't do more. All right, let's just look at the answers and see if I can spot a pattern. All right, 6. So 5 weighs 1,935. 6 weighs is 1,944, so it's basically 9 more than the n is 5 case. 7 and 8 probably are twice 9 as well. Yeah. So if I can do one type of case, I can probably do the one that's like one more than that. And then for 9 and 10, okay, sure. So what is the formula here? 1,935. I feel like this probably is a power of 3 deal. So this went from power 3 squared to 3 to the 5th. So maybe 3 to the 8th. Unfortunate. So it's not 3 to the 8th, although it's on the order of 3 to the 8th. It's not 3 to the 9th either. So what is the complication here? It goes from 9 to 252. So it's not like it goes from 9. So what is the deal here? When you have another digit, actually, am I doing it right with k is 1 and 2? 1 and 2. Let's get rid of just case 1 and 2, I guess. 1 digit 1, 2 digits 1. Should both be 9. Yeah, 9 and 9. Although that is kind of weird that it doesn't increase by 9 like the other ones do. Like the 3 and 4 case. 3 and 4 case. Which is 243, 252. So it's not like it's offset by 1. Like you start with a 9 always, and then you do start with 9 always. Huh. What if it was... Yeah, that's a big jump. Alright, let's just compare the jumps here. 1,935, 10,935 divided by 252. So factor 43. And then the next jump was 617,000 divided by 10,935. So pretty big jump factors. And then this one, $67. All right. So this one was 256 divided by 26. It was 9, right? Roughly. 252 divided by 26. I think that's roughly 9. Interesting. Okay. How to approach this? How to start counting here? So n is 5. The total is going to be 10,935. And so if it was similar to how it did this thing, I assume this has to be divisible by 9. 10,935 divided by 9. It has to be divisible by 1215. So there's going to be 1215 ways of doing 1 followed by some set of numbers. So how to get those 1215 ways? So those set of numbers would be 1. Okay, let's say it starts with 1. Do I leverage good numbers to make other good numbers? So if I have a 4-digit good number, I should be able to add a 1 to it and make it a 5-digit good number. So yeah, I think that's reasonable. So 4-digit good number plus a 1 is a 4-digit good number. 4-digit good number is guaranteed to have like some, in the most common case, 2 pairs of 2 digits. Sometimes it's all 1 digit. And then there's the extra case where the 4-digit good number, or the 4 digits, could possibly have started with zeros, or could have been all zeros. And technically that wouldn't be a good number, but it would work if it's plus 1, like 1, 0, 0, 0, 0. No, actually that doesn't work, right? The palindrome doesn't include 1, 0, 0, 0. Like you can't rearrange it from 0, 0, 1, 0, 0. So you're dealing with 252 possible 4-digit good numbers, and then you add 1 to that, or well, you add a 1 to it, so that's 252 waves. And if you multiply that by 9, that gets you 252 times 9. That gets you 2268. So not even close to 10,000. 2268. But then that doesn't include zeros, or it doesn't correctly account for zeros. So we have a 4-digit good number. There's 252 ways of doing that. And then if you add a 1 on top, all those ways are unique. All those 252 ways are unique. So if you add a 1, that's the leading digit. That would also make it a unique number. But why is it so short? Like it's a factor of 5 short, roughly. 2268 versus 10,000. So I'm missing something here. If you have n equals 4, 252. And then I'm missing the zeros. Somehow the zeros are, I think, really bumping those up. Somehow. I mean, what other things could it be missing? If you're dealing with okay, so what good numbers could work from a pair including 0? The zeros should only be like another. So the 252. So what? How do zeros add to count? Hmm. 1215. Yeah, so it's like there should be 200. There should be 1200 ways of actually forming a 1 and then 4 digits. But I'm currently only getting 252. 1215. So I'm missing like a factor of 5. 5, 1, 0, 0, 0, 1. That works. What if I used n is 3 or n is 2? N is 2. N is 3. Then it'd be 1, No, it's not. There has to be 2 zeros, possibly. Can't just be 1 0. Well, it could be 2 zeros or 3 zeros. Or 1 0. Like it could be. Could be 1 0. Oh shucks, I'm gonna double count stuff. Not good. So it could be 1 0 0 1 1 1. Like 1 1 1 0 1 1 1 isn't part of it. Isn't part of the 4-digit good numbers. Or it could be 1 0 0 1 1. Because 2-digit 0 0 1 1 doesn't count. Isn't part of the good numbers. 4-digit good numbers. It could also be 1 0 0 0 1. Oh, I see. Is it similar to 1 plus any good 4-digit number plus any good 3-digit number plus any good 2-digit number plus any good 1-digit number? Like 240, 252, 243, 99. That's still short. That's still short. 252, 243. That's still short. A half. 1215. 513. Yes, it's still short by half. But it's getting there. Is 1 plus any. Actually, so let's say it's like 2 3 2. Can I even make a pound from that? Alright, that doesn't work at all. So it's not 1 in any good 3-digit number, any good 3. 1 plus any good 4 works. 1 plus any good 2 works. But 1 plus any good 3 doesn't work. 1 being the 10,000 spot. So it's just 1 and it's just 4 digits and the 2 digits. Okay, is it in between digits would be zeros, of which there'd be 0, 2 zeros. And then, so what works with 1 0 XXX? So 1 plus good 4-digit is good 5 digits. 1 plus good 2-digit has to be a good 5-digit as well. Say 10,000. So that one's in the 10,000 spot. So we have 10,000. We have 10,000 plus. It has to have another 1. So the x needs a 1 and needs any other 2, I think. So it could be 90. It's a 1 and any other 2. So there's 10 possibilities there. But then you double count the zeros, I think. So it has to be like P1P. It doesn't have to be. It has to be something that includes 1 and then 2 numbers that are the same. So is that not 27? 1 and 2 numbers that are the same. So it could be that, or P1P, or PP1. So there's 9 ways of doing this. Is there 9? Oh, there's 9 ways of doing this where P is not 1. Or P is not 1. 9 ways of doing this, and then 9 ways of doing this. I think this ends up being the same thing as this thing. Say what? Yeah, so this is 27. So this first way is just 252. And the second way is 9. And this third way is 27. Has to have 1. And it can't be 100. Or can it be 100? The P here could be 0 through... Okay, so the P here could be 111. Yeah. So there's 10 ways of doing this if you include the ones. P being 1. But 9 ways if you don't include P being 1. 9 ways of doing this if you don't include P being 1. And 9 ways of doing this if you don't include P being 1. So plus another 1, because all of them could be 1s as well. So that's 28. Plus, so there's 28 ways. This is still so much shorter. This is still short a lot. $252 plus 9 plus 28. $289. And if you have 1215 divided by 289. 420. And then if you have like 1001, if you have just one digit, then it could be any digit besides 0. No, actually, the last digit, if it's one digit, it has to be just 1. Like, nothing else works, right? So if it's a 1, 1, it has to be a 4-digit number. That's good. So those 4-digit numbers would be 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. If it's a 1, 0, then it has to be 1, 0, 1, 0, and then some pair of numbers and rearrange with p is 1. rearrange with 1 is somewhere in that. Is there only 27 ways of doing that? So 10991 be part of this, or 919 part of this. So there's 28 ways of doing that. 252. Man, I'm so short. Like, how is it this short? All right, 4 digits. 252 ways, not including leading 0. What if you did? Man, that fucking leading 0 shit. Feels like the solution should be some form of recursion where the cases go downwards, where the number of digits uses the number of digits of 1 less. Or maybe you should use the one that's 2 less. Maybe use both. Maybe it uses both. So for instance, if you have a 3-digit number, that could be formed from a good number. A 3-digit number could be formed from a good 1-digit number. Could be formed from a good 1-digit number wrapped around plus some extra digit. So 3 digits using 1 digit plus a pair. So let's consider this. So recursion idea. So like a 3-digit is going to be based on 1 digit plus pair, or something with 2 digits. Based on one digit good number plus 2-digit good number. Some calculation based on that, and then 4 digits based on a 3-digit good number plus a 2-digit good number. And then the 5 digits based on like the 4-digit not ordering based on this, 2, 3, 3, and 4. And there's, in theory, that could work maybe. And this is all strictly for k equals 1 too. I have to generalize it to where k is bigger. So 3-digit good numbers. There's 9 1-digit good numbers. And there's 9 2-digit good numbers. And a 3-digit good number could be wrapping, could be creating a palindrome from wrapping a 1-digit good number by a pair, then a 2-digit good number by a single number. And then a 4-digit good number could be wrapping the 2-digit good number by a pair, and a 3-digit good number plus, well, 3-digit good number, just can't add any number next to that. It has to be the number that pairs with the, with the singleton. It has to be a number that pairs with the singleton. So 3-digit ends up being 243. So why doesn't this idea work? So if it starts with a 1 and it has to be a 1-digit good number, well, so it would either be 1x that number or 1x that number if it starts with a 1. So that good number, that is, no, so what am I doing here? So the 1-digit good number, you can put that 1-digit good number. You can add a pair either as like xxd or xdx or dxx, or that d is the 1-digit good number. And then 2-digit good numbers, you can add, well, it would be the same kind of dxd or ddx. Then there's so many overlapping cases here. If they're not distinct, they're not disjoint counting. Oh my god. Why is this so hard? Three, 4, 3. 10,955. If you take the palindrome what you're really worried about is the number of ways to form a 5-digit palindrome is there has to be one number that is, there has to be like two pairs. There has to be two pairs and a singleton. Or if there's a 6-digit palindrome, there has to be 3 pairs. Again, the pairs can be duplicate. So it could be 1, 1, 1, 1, 1, 1. And then you have to rearrange it so that the leading values, no, you have to rearrange it for the leading values to be anything. As long as the leading value is not 0, you can have as many zeros as you want. So one of the pairs has to be non-zero. Or not all the pairs can be 0. But then you can't rearrange the palindrome so that your first numbers are zeros. So even if you have like 4 zeros and 2 ones, it could be 1 0 0 0 0 1, but it can't be it can't be like 0 0 1 1 0 0. Not if you wanted to count it as 6 digits. What if you for 6 digits, what if you did just count it including leading zeros? So you did it count including leading zeros, and then somehow subtract out the number of ways that you have leading zeros. I wonder if worrying about this 6 versus 5. If I solve either case, I can solve the other case. It's just adding 9 or subtracting 9. So which case is simpler for me to consider? Probably the evens. So if you have an even number of digits, okay, so we're just going to ignore, So the one thing I got from this is total for n equals even is n equals odd is total for n equals odd plus 1, total for n equals odd plus 1 is total minus 9. Total. Minus 9. Alright. At least I understood that. Or at least I got that. So I just need to solve one of those two cases. And I think it's easier to solve for the total. Solve for, well, except for n equals 2. That's just okay. So I'm going to solve for n equals even. So they're always divisible by 9. So the total will always divisible by 9. which makes sense because there's 9 possible starting first digits, and they're all kind of symmetric in that way. So really I just need to solve for where arbitrarily it starts with 1. So solve for where number starts with 1. So starts with 1. Let's say again let's say n is 6. That means you have a 1 and another 1 somewhere in the palindrome, and you have either 2 pairs or a 4 of a kind, where the pairs could include 0. So it'd be 1, 1 plus 2 pairs. Well, the 2 pairs, there's 10 times 10 ways of doing that. And how many ways can you rearrange the order of those things? How many ways can you rearrange the order of those things? So there's 4 digits in 5 spots, not including thousands, the 10,000 spot. So the 1 can be, man, this feels like this is the wrong way to count it because it's not distinct, not disjoint. Because otherwise, if it's just 1 in one of the 5 non-10,000 place, then it'd be 5 ways of picking that. And 5 times 100 would be like 500. But it doesn't quite work. 2 pairs. So 10 ways of picking the first number, 10 ways of picking the second number. Let's not choose 2 because you can pick the same number. But it could be symmetric. You could be picking 2 zeros or 2 pairs of zeros. And if you pick 2 pairs of zeros, then there's no distinction between the pairs. Oh gosh. So if you pick 1, 0, 0, and then another 0, 0, 1, 1, 0, 0, 0, 0. Or it could be 1, 1, I wonder. So if you have 1, if you have 1, this is all caked. And it still looks so much like a 5-digit good number. 5-digit good numbers and 6-digit good numbers are very... I can't really leverage that case because I'm solving for one or the other. It's either it's actually using the 4-digit good number or the 3-digit good number that could possibly have a different result from. Well, if I use a 3 or 4-digit good numbers, I mean, it's pretty much the same because 3 and 4 are just off by 9. 3 and 4 are just off by 9. You have a 1-digit. I know the number of things that start with 1. That's a good 4-digit number. It's 4-digit case divided by 9. Right, 4-digit case, 252 divided by 9, which ended up being 28. So it ended up being 28. And then, so that's 28 good 1-digit number that starts with 1, or 28 good 4-digit number that starts with 1. It doesn't have to start with 1. It could be, well, so for 4 digits, maybe I should be using 5 digits. So that's the one that actually is more closely tied. So solving for 5 digits. So 1, and then you deal with 4 digits. Right. So it'll be 1, and somewhere in here has to be something that has a 1 in it. So it could be something that starts with a 1. But then if it starts with a 1, it has to include another 1 within it. No, why does it have to start with a 1 at all? Any 4-digit good number works here. Any 4-digit number works. 4-digit good number works here because it has a pair, and the 1 could be somewhere. 1 could be placed in the middle of the palindrome after the rearrangement. So again, that ends up being 252. And then it could be if it's a 3-digit good number, this would end up being 10, 3-digit good number. Could that be a 1, 1 here, where the 3-digit good number is not part of the 4-digit good number? So like 1, 1, 2, 3, 2. 1, 2, 3, 2 is not a 4-digit good number. So yeah, 1, 1, 3. So if the 1 is duplicated here, or like the 3-digit numbers could be there, or could be there, or could be there, be there. So the order matters, but that ends up being maybe 243, 243, 243, 243. 243 times 3, 729 plus 252, 981. Okay. And it was that I wanted to end up being at 1215, was it? 10,935. 10,935 divided by 1215. So 243 times 5 plus 9. 243 times 5 plus 9. 243 times 5. It's literally 1215. And for some reason, I don't worry about having 3 ones. Or maybe I do worry about it, but somehow negates itself in this calculation. So, no, so this is not right. This is 252. That is exactly 252. So, what is the thing here? If you have 252 times 9, include, so 1 in the 10,000 plot plus good 4 digits would be 1xxxx, and then 1 in the 10,000 spot plus good 3 digits. So that means that you need another 1 in the 1,000 spot, 100 spot, 10 spot, or 1 spot. But then the here can be all ones, right? It could be all ones, and they would be duplicated. The 243 case includes all ones. In which case you have 1 extra that's the same. That's overlapping between all 4 of these possibilities. So overlapping case. You have to count. You have to take into account that, otherwise you're going to miscount. So 1 plus good 4 digits. That has to be 252. Am I missing? I've seen the case where it's like 10011, because 10011, that is a good 5-digit number that doesn't fall under 10,000 plus a good 4-digit number, because a good 4-digit number doesn't include 0011, nor does it fall under 10,000 plus a good 3-digit number, because a good 3-digit number doesn't include 011. So I think it has to be something where this thing is this thing is overcounting in this area, and then that overcounting is compensating for the undercounting of something like this. So it could be 1 0 1 1 10,000 plus a good 2-digit number. And there's exactly 9 ways of doing that. Well, there should be 9 ways. It can't be all zeros. And then 10,000 plus a good 1-digit number. And again, that can't be all zeros because you can't have just 10,000. So there's 9 and 9 ways of doing this. So like 10,011, 10,022, 10,033, 10,044. Like all those ways can rearrange to like be some number non-zero, 0, 1, 0, some non-zero number. And similarly, if it's a good 1-digit number, no, it has to be 10,000 plus. The only good 1-digit number is 1. So there's just one way of doing that. Only good 1-digit. Huh. So somehow it needs to get back a single 1 here. Alright, so 10,000 plus a good 4 digits. 10,000 plus a good 2 digits. 10,000 plus a good 3 digits. So if it's 10,000 plus a good 3 digits, it needs to incorporate another 1 plus another 1 somewhere. So that somewhere could be 1 1 or 1 x 1 or 1 x x 1 or 1 x x x 1. So if it's x x x, this thing is over counting by 9. So good 4-digit number. So good 4-digit number. This includes 1111. And then the 11xxx. That also includes 1111. This includes 111 here, and here, and here. So 252 plus, now I'm overshooting it. It's 252 times like 251 plus 243. So close. 12, 15. $252 includes 1111. 11111. that the only case where it's all overlapping? Good 4 digits. So good 4 digits starts something. Good 4 digits could be 1 and starts with 1. That overlaps with 1, 1, x, x, x. So there's some overlap there. So this thing right here overlaps with a good 4 digit that starts with 1. Alright, so the overlap there, how much is the overlap? Is it 200? I mean, is it all strictly overlap? No, right? Things that are 4 digits that start with 1 would be 28. 28, 4 digits, good 4 digits, starting with 1. And that's from 252 divided by 9. So I think that overlaps 28 times. Because otherwise the good 4 digit would be like 1, 2, 1, 1, 2, or 1, 2, 2, 1, 1. Something where it doesn't. The 28 would overlap with the 1, 1. Does it overlap? It overlaps in the sense that there's 2 1s starting. But here this is going to be a total of 3 1s. Possibly 3 or 5. And here this is 1, 1. And then 3-digit number doesn't necessarily need to have another 1. It would have to have another, it would have to have the middle number be 1. Singleton be 1 in order for it to overlap with this one. So that'd be 243 divided by 9, which is 27. So there's 27 numbers in there that has a singleton 1. Oh man, this count is, there's just no way I'm doing this correctly. Alright, time to look up a hint. How to generate all palindromic strings of length n. Do we need to go through all n digits? Need to go through all n digits. So I guess what they're trying for is to actually go through some set of possible values. Check if that is divisible by k, and if it is, then what is the deal here? So how to generate all k palindromic strings of length n. Do we need to go through all n digits? So maybe k being 1 is not how I want to approach this. Something simple like k is 5 might have been a lot easier. Although let's just go and just do a quick check here. N is 3, k is 5. $27, $52, $22.31. Big numbers. It's actually bigger than the. Seems bigger than the divisible by 1, really. How are they bigger than divisible by 1? Oh, this is 3 and 4. For 3, when n is 1, it was 50. It was 250, 243. This was 252. 27, 52. Something like double. This is a lot of numbers here. Like this is in the millions. Yeah, this is 19 million. That'd be too slow to go through individually. Note that any so the integer is called good if it's divisible by k. So what if you had what if you went through what if you had an array of digits and what if you had an array of digits where I'll generate all k palindromic strings of length n. Do we need to push? Do we need to go through all n digits? So in theory, you can go through half the n digits because the other half has to be the same. So it's how many numbers that are divisible by k in half the digits. And it doesn't have to be the same. Well, it does have to be the same in order to make it a palindrome, but then that's just the number itself and which digits that you're dealing with. And then you need to figure out how many ways to rearrange those digits. So, oh gosh, I think this was worth a shot, but here, determine the number of ways theory, number of multiples of k in with n divided by 2 digits, since those digits will be duplicated. And then determine the number of permutations of that set of digits, and possibly ignore anything that's already been seen. Ignore anything that's already been seen. Seems like a lot. So you could go through incrementing by k for values between 1 and n divided by 2. Values between 1 and n divided by 2. As long as all the numbers are not all zeros, then the rearrangement should be possible. Or as long as all the numbers include a pair of numbers that are not 0. Because this just includes one non-zero number, like a singleton 1, and the other things are all zeros, then that wouldn't work. Count the number of good integers. So, I mean, that would at least lower it down to from 10 digits would be 1,000,000. That would lower down to 500,000. 500,000 is still long. A lot of numbers. Oh, let's go ahead. Let me just see this. Let's say for num in range up to, so it has to be 5, so it has to be number n digits from n digits to n times 5 digits. No, n, let's say n is 2. So you're dealing with something from 10 to 50. Half n to the third power. Starting with 10, going to 50. If it's 4 digits, if it's 3 digits, then it starts from 100 and goes to 500. And if it's 4 digits, it goes from 1,000 to 5,000. guess. So let's say the low is 10 to the power of n. So it's one digit, no, n minus 1. So if it's one digit, n is 1. 10 to the 0 power is 1. If n is 2, it's 2 digits, it would be n to the 2 minus 1, which is 10. 3, 3 minus 1, 2, 100. The high would be 5 times the low. So anything from 5 times the low plus 1? No, it's from low to high plus 1. I think. Yeah, not be right. Anything from the low to the high. What if you went skipping by k? What if the low number was the first k multiple within that range? Let's say low is actually going to be low divided by k times k. Ceiling of this. Python ceiling. Math.ceil. So that guarantees that the low is actually a multiple of k. And the high is 5 times the low. If num mod k equals 0, print at num. Alright, let's go ahead and see if this works in terms of just printing out the stuff. So let's say n is 2, n is 2, n is 3, k is 5. Should print out a lot of stuff. Yeah, so 3-digit numbers that are multiple 5s, and 2-digit numbers that are multiple 5s. Up to the halfway point. I don't think the halfway point is correct. Because it's not really halfway, not really doing halfway digits, you're doing halfway bounds. So it's a palindrome. Palindrome, you should be doing halfway bounds. Or halfway digits. So if it's 3-digit number, then how many digits is halfway? It's just 1 digit. And if it's 2 digits, then it's halfway is 1 digit. Halfway 1 digit. Wait, then if it's a 1-digit number, it's a one-digit number, you're still testing whether or not you still need to test whether or not the palindrome is actually divisible by k. You know that you can look at half the digits in order to determine whether or not it could be a palindrome. But you still need to look at all the digits to determine whether or not it's divisible by k. Alright. It's time for hint number 2. Use permutations to count. Oh my god. Fuck. Alright, so how to generate all k palindromic strings of length n? Do we need to go through all n digits? Well, apparently not, since that's the hint. What is the length of palindrome? Palindrome is an integer that reads the same forward and backwards. Excellent. Integer x is called k palindromic if x is a palindrome. Do we need to go through all? Do we need to how to generate all k palindromic strings of length n? So here the hint doesn't actually say generate all palindromic strings of length n that is also divisible by k. No, it's k palindromic. So how to generate all things that are divisible by k and also palindrome. So you can go through multiples of k that are in the range from low to high, where low and high are based on the number of digits. And then you can check individually whether or not each one, you can do that on the multiples of k. And then you have to check individually whether or not it's a palindrome. And then even there, you have to store that, because then you need to do permutation computation. Seems excessive. It also seems very slow. I mean, that's a big number of numbers. 1,000,000? I don't think you need to run 1,000,000 times, or 1,000,000 divided by k times. Save a number. You have a number. And you each number. Each number. How is there's this high acceptance rate? That's crazy. 41%. Each number you add palindrome. So your first and last digit are the same. Second and last digits are the same. Second to last. Third to last. Fourth to last. Fifth and fifth to last. So if you're dealing with palindromes, then you're going to go through for all the, so for each digit, really, if it's a palindrome, then how many things do you have to look at for? If it's at most 10 digits, then you're going to have 5 digits that you're really working with. Because the first one maps to the last one, second maps the second to last, third maps third to last. There's really 5 digits. Can you use a so, and each of those 5 digits has 10 possibilities. So could you do maybe a for loop that runs where the outer loop goes through the digits, the inner loop goes through the outer loop goes through the spots, the inner loop goes through the digits. Goes through the digits at the spot. It would still run 10 times 10 times 10 times 10 times 10. No, you can do that, can you? You have to do 5 loops in outer for all the ones digit, and then for all the tens digit, unless you do backtracking. For all the ones digit, and then for all the, so you do a backtracking loop. Still runs. It still is going to be 10 times 10 times 10 times 10 times 10. That's 10 to the 5th. So that'd be 10,000 things. Then you still need to track the permutations. And you need to track whether or not you've already seen that permutation. So if you did generate all possible k palindromic strings of length n. So you have an array of digits of size n, and then you go through half the array and set the index at some spot in the array plus the index in the back of the array at that spot to be some digits. See if that's a palindrome. Well, you know that's a palindrome. You see whether or not it's divisible by k. If it is divisible by k, then what? Then you need to store the number of ways you need to store that unique combination, because that unique combination cannot be used again. Like, I guess you can store that unique combination by the ordered ordering of those digits. And then from there you add onto the answer, if there's a new ordering, you add onto the answer the number of ways you can order that. Okay. Wonder if this is going to work. So digits is an array. Let's say 0 times n. So if n is, let's say 10, then it's a 10 size array. Then I'm going to do, I think I'll use a backtrack. And it's going to be the spot, the place value. I'll have an answer equals 0. I'll have a combos set. And I guess it can't start with 0. Well, can it? So starting digit has to be 0. So digits of first, well, for all start in range 1 through start digits of start. So the starting digit is going to be digits of 0 is the start, and digits of the last is the start. And I'll do the backtrack for everything between. So if digits of the start 0. I think I call backtrack. I think this needs to be self. Self.backtrack. What is the place here? Places has to start with 1. And I think that's it. And then return the answer. And then here it's going to be what? Here's going to be if the place is past the 3 spots. So technically the number of free spots is 2 less than, because I'm already setting the first and last spot, so it's 2 less than n. So I'll say here that the max spots is going to be n minus 2. Maybe I should call this place value, max places. So if it's a 3-digit number, then there's one place in the middle space. If there's two digits, not including the first and last digit, then there's no places. So if the place is equal to the max place, well, is equal to or less than or equal to, greater than or equal to. Because if you're dealing with a 1-digit number, there's -1 places. So 1 is bigger than -1. If you're dealing with a 2-digit number, there's 0 places. And 1 is bigger than 0. If there's a 3-digit number, then there's 1 place. So max places is n minus 1. 3 minus 2 is 1. If place is greater than 1. Yeah. So place is starting with like the second digit in the number. So 4, n is 4. There's 2 free places. No. So if n is 4, there's actually only 1 free place because that 1 free place matches with the back half. So it's n divided by 2 minus 1. Places is n divided by 2 minus 1. So 4 also only has 1 place. 4 has n is 4, you have your hundreds and your tens place in your palindrome that is 3. Your thousands and your ones place set the starting loop. First digit is non-zero. Similarly, last digit is non-zero. And then you start your second place. The number of free places is half your number of digits minus 1. Minus 1 being your subtracting out your first / last place. 3 being something that includes 0. So if the place is greater than the max place, then you need to determine if palindrome is divisible by k. If so, add to combos. If new to combos, add permutations to answer. Okay. So how do I determine if it's divisible? I think maybe this backtrack should include like a value. So the value of the array in addition to does it need to include that? So otherwise you would need to convert the array to a number using a for loop. If you didn't do that, then you could just add or subtract values or add values to the palindrome currently. So maybe I don't want an array. Maybe I just want Maybe just one number. Array makes it simple, but a number is a number might be more flexible. So how would I do a single number? Also, a single number has a slight issue where if n is 1, then you're not necessarily adding. Well, n is 1 is kind of a trivial case. Okay, so let's say the actual value is being passed. The value is 0. And the start is going to be the value, the first digit of the value is that number. So start times 10 to the power of n. So n is a 1-digit number. And then, or let's say 10 is a 3-digit number. 10 to the should be 1 times 10 to the power of 2. So the start is a 1's in that spot. And then that's your baseline. And then the value plus equals your start as well. So like 101 or 202, 303, 104. So that's your values to start. Okay, so and this is going to be where the first digit is non-zero. And this is one's digit is matching non-zero. And you're now backtracking to the second spot in your number starting with this value. Okay. So now if n is 3 and you're passing in the place value 1, you're dealing with the tens digit. You're dealing with the tens digit. So you want to go through all the possible pairing of this place at this, and pairing of this place and the place across from it in the palindrome. So say other place is going to be n minus this place. So if it's 10 to the third, this can be hard for it's gonna have to handle the case of this needs to handle the case of odd versus even places, or odd versus even n, because the place could be in the middle and you don't want to duplicate that. Okay. Handle base being middle. Handle edge case. Replace is middle digit. And then handle normal case. Common case, where place is not middle. Okay, so other place would be, so let's say n is 10. So if you have 1, which is like your 100,000 spot, then the other place would be your 10 spot. So if you have 1, so the 2 places here would be, let's say PV1 is going to be 10 to the power of n minus place, where this is the first place value. And PV2 is going to be 10 to this place value. I think it's n to the n minus 1 minus place. So if you're dealing with n is 4, so let's say n is 4, so you're dealing with 4 digits. So here, when you make the call, the place is going to be 1, which is going to affect the 100 spot and the 10 spot. It's going to change hundreds and 10s spots, or 10's place value. Places. PV1 should be 100, PV2 should be 10, where PV1 is 10 to the power of 2, which is equal to 10 to the power of n minus 1 minus place. And this is, what place is 1? It's 10 to the first, which is 10 to the base. Okay, so that's that. So those are the place values that you're changing with this palindrome. And then basically go through all the possible values for every possible in range from 0 to 0, 10, so all the digits. The value, the palindrome, let's say the base, the current number is going to be the value plus PV1 times this possibility plus PV2 times this possibility. So this goes from so it goes 1001, and then possibility 0, so it tests 1001. But then it needs to actually go through and backtrack further. Self.backtrack place plus 1, and this current number used as baseline. So this goes, so let's say n is actually 6. So it starts with 1001 with 4 zeros between 1001. Then it's going to change this place value, and this place value becomes 0, and then go on to the next call where it changes these values between 0 through 9. Alright, so then it moves on further. So it calls this thing. Alright, so now let's handle the handle the handle where it reaches the end of the backtrack. So if the place is greater than or equal to the max place, so if n is 6, there's basically 2 places that you're dealing with that you're free to try to mess with. And then if n is 3, if the place is 3, which is half of 6, which place is free when n is 5? 1000. Which place is free when n is 5? So I think you have 2 free spots. This place value, which affects that place value, and then this one, so it's 3 as well here. So the max place should be n divided by 2. 5 and 6 both have 3. So it should be n plus 1 divided by 2. So if n is 1, 1 plus 1 divided by 2. Yeah. So if place is equal to the max place, then no backtracking if reached end of possible places. So at that point you just evaluate whether or not the value itself is divisible by k. So if and then return. If the value is divisible by k, then check to see if this combination is there. Fuck! This is where the array would be useful. I guess what you do here is you convert to a string, sort, and add. So convert to a string, see if that string is already within the place. The value mod k is 0. Yeah. So you digits is going to be equal to the list of the string of this number, sort the digits, and then add it to and then let's say string digits is going to be sorted version of digits, the string of that. And sorted Huh. Go back to the array? Going back to the array is okay. It's probably pretty uncommon that I have to do this. It's more common that I have to do this. It's more common that I do this. This would be affecting the array of digits. Once I have my array of digits, maybe I have both the array of digits and the value of the values in digits array. Maybe I have both. So I don't have to convert each time, but then I can quickly use the array. Alright, so let's see how this one goes first. If the value mod k, so if it's divisible by k, that means value is k palindromic. K palindromic. Then I convert the value to a string. Convert that string to a list of digits, letter characters, or digit characters, and then I sort it. I think it's just casting it, right? Yeah. And then string of the digits sorted. Sort the list. And then if string digits not in my combos, in combos.add this string, and then I need to add onto my answer, and then I need to return if place is equal to my place. Okay, self.answer. So how many ways can this be? How many ways can this be done? So I have a palindrome. So the number of ways you can rearrange the palindrome, the digits of the palindrome, would be what? I think it's the depends on how many unique letters there are. So if you have let's say 2 duplicates, let's say you have 2 1s and 4 2s, 2 1s and 4 2s, then Oh shoot. I wonder if this is too many things to keep track of. Hopefully not. Could be a lot. So I guess I could maybe convert it to an integer. String the digits, and I can make this into integer. And then sorted num integer version of this. Convert string to integer. I think it's just the straight cast string, right? So sort number is this integer of the string digits. And then yeah, this should be less space. Instead of a bunch of strings, it's just a bunch of numbers in the hash. Okay, so if it's say two ones and 3 and 4 twos, how many ways to permute that? Well, if we're doing permutations of 2 ones and 4 twos, it doesn't really matter. First number can't be 0. Do I care? Here, starting number being non-zero. Yeah, I guess I care because I'm creating the palindrome there. But here I just need to determine number permutations where it doesn't start with 0 if there is 0 within the sorted set. Doesn't. Huh. Sorted numbers. I wonder. So, what happens? What happens if I did something like, say the value is 100. So let's say print. Let's say the digits there is the list of the string, this value. String digits is equal to sorted that convert to a string. Sort number is the integer version of that. Go and print out everything. Not answer. Unexpected indento. Okay, yeah, so string of digits. So currently, can I convert an integer to a list? Okay, so that's how I do it. Integer d for each d in the string of the number. So I need to convert to a string anyways. Digits to a list. And then convert each. So the sorted number, string of the digits is that. And the sorted number is the integer of so converting from a so maybe I should so I really don't care about string digits, right? So I can just do digits is the list of the string, the integer of the digit for each digit in the string of the value. And then I can sort that s digits. It's going to be sorted of digits, and then I can convert how to convert that back to number. So I can convert the well, I don't need to convert that to so if I have a bunch of digits sorted, then I can say sort number is I don't know, the sum of all the 10 to the power 10 to the power of take each digit. Oh gosh, there's probably something straightforward for this. Bring the digit in my list. Join. Reduce. Lambda expression. So this becomes 36, and then 365, and then 3,658. Reduce lambda xy, x times 10, y my list. Okay, that seems reasonable. Sorted number is reduce lambda xy for x times 10 plus y for digits. Okay, I think that might work. Oops, should be sorted digits. Okay, so the value is 1,000. The digits is 0001. Sorted is 0001. The digits is 1000. Sorted is 0001. Then if you reduce it, if you reduce the sorted digits, you reduce it becomes 1. Okay, and then you add 1 to your combinations. But then when you look at your permutations, you see that there's some number of zeros and ones. First number cannot be 0. First number can't be 0. So first number can't be 0. How do you calculate that combination? So let's say the number was 1, 1, and 4 zeros. Well, technically there's no way of doing that. Right. Technically that's not even a palindrome. Let's say the number was 1,000, or 2 ones and 5 zeros, 4 zeros. 2 ones, 4 zeros. So the number ways of doing that. Number permutations of 2 ones and 4 zeros. Well, you do 5, 6, choose 5, choose 1. Because the 1 has to be in the first spot. 5 remaining spots says 5, choose 1, and then 4, choose 4. I have a bunch of combination. No, you should be able to do it some other way. So I think the other way of doing permutations with repeating stuff is n factorial divided by n factorial divided by the number of, for each duplicate, the number of that, the count of that duplicate, the frequency of that duplication factorial divided by that. Then you also need to not have the non-zero in the, also need to have a non-zero in the first spot. So So it's like 6 factorial divided by 2 factorial divided by 4 factorial. Okay, so let's say n is 6. 2 ones and 4 zeros. So permutations is going to be n factorial divided by 2 factorial, 4 factorial. But that includes ways of having 0 at this front. If you don't have 0 at the front, then what? And you have what is that? 6 factorial divided by 2 factorial, 4 factorial. 720 divided by 24, 30 divided by 2 is 2, it's 15. So there's 15 ways, but if you have one, there should only be 4 ways. 1, 0, 0, 0, 1, 1, 1, 3 zeros, 1, 0, 1, 2 zeros. So there should really only 4 ways. So how do you divide out? You can't even divide out 15 to become 4. 6 factorial, 6 numbers. Divide out 2 identical ones, 2 identical zeros, or 4 identical zeros. So that's 16, or 6 factorial divided by 24. 4 factorial is 24. 6 times 4. Divided by 2 factorial is 15. What if it's the case you have 1, 0? You know you have to start with a 1. So there's only 5 spots remaining. And then you know you have to use 1 for the 5 remains. 5 remains. So there's really only 5 answers. So you need to divide by 3 here. Why does 3 make sense? Because of the, so you have a 1, 4 zeros and a 1. There should be 5 different, so you have a 1 and then 5 choose 1. This should be 5. So if you do 6 factorial, 2 factorial, 4 factorial, so it's actually 5 factorial, right? Out of the 5 different spots, it's actually 5 factorial. And divide by 1 factorial, 4 factorial. So 120 divided by 24. Yeah, 120 divided by 24. Because the 1 is not part of that calculation. And that gives you 5. So what if it's more complicated? Let's say that's 2 1s, 2 2s, and 2 zeros. Oh god. Okay, so this is 5 factorial divided by 1 factorial, 4 factorial. This excludes 1 and first spot since 1 is required there. So let's say it's 2 1s, 2 1s, 2 2s, and 2 0s. So what's the calculation there? So either the 1 or the 2 is in the first spot. So it'd be something like the number of non-zeros choose 1. So it's like 4 choose 1 times the number of ways to make the rearranging the rest of it. No, so the number of non-zeros is 4 choose 1 and then 5 choose 2. I'm not even doing the permutation way of calculating this. Fuck. Oh. It's less like, sometimes I don't even know where the computer science part of this is. This is just like fucking fucking counting the number of ways of doing things. Are there even companies that would use this as a fucking tool? I guess if they want all their engineers fucking geniuses. And then some. Right. So you have a list of digits. Just need to calculate the number of ways of getting permutations. Number of ways of getting permutations from a list. Use permutations to calculate the number of possible rearrangements. So what if so the number of of the spots that are not leading, there's a factorial number of ways of doing those. And the zeros really suck. Alright. The base is equal to the max place. The value mod k is equal to 0. So if you have a palindrome that is divisible by k, how do you determine the number of permutations of that palindrome? The number of permutations of that palindrome. Use permutations to calculate the number of possible arrangements. Well, do I even need to? I guess I'm going through all the possible. No, I do need to because I'm going through the palindromes right now. And the non-palindromes can be anything. Use permutations to calculate the possible rearrangements. Use permutations. All right. Not a great hint, I don't think. So if we get the count of the number of digits, like for instance, from here you print out counts of the sorted digits, or counts of the digits, counter of the digits. Yes, there's 3 zeros and 1 1. And then from there, how do you determine the number of permutations just based on the frequency of zeros, ones, and all the other digits? Knowing that you can't actually have a permutation that starts with a 0. Man, this is fucking not trivial, even in the sub problems to this problem. So your first digit can't be 0. So you go from the number you go through so you have some number of non-zeros. So you have some number of spaces that are for the zeros. So you do something like n minus 1 choose the number of zeros. So that chooses calculates the number of ways to put zeros into those spots. And then you have a remaining number of digits for your non-zeros. And you can do the factorial of that divided by the, so it's like n minus 1 choose your number of non-zeros, or n minus 1 spots, choose some number of spots for your zeros. And then for the remaining, it's the remaining n minus 0 factorial, n minus number of zeros factorial, divided by, for each duplicate, the factorial of that duplicate, for each non-zero duplicate. Oh my god. Okay. How do I quickly determine combinations? Python combinations function. And choose R. What is math.combinations? Math.combinations. Okay, so the combinations add that sorted num answer plus equals. So for the sorted num, right? So I need to go through digits, and then the sorted digits is equal to the sorted of the digits. Sort the num by reducing lambda xy, x times 10 plus y, sorted digits. Okay, and then from that point, if that sorted num is not in combinations, then I'm going to create the counter of the digits, and do here. So number of ways equals 1, and then ways equals 1, and the calculation is going to be ways it starts with math combination n, so zeros is counts of 0. So math.combinations n minus 1, choose some of them for your zeros. So if there's like 6 spots and there's 4 zeros, and of the 5 remaining spots that are non-leading, choose 4 of those spots to be for the zeros. And if there's 0 zeros, then it'd be like the number of choosing 0 just 1. I think. Yeah. And then for the remaining spots, you multiply it by the remaining. So ways times equals n factorial. No, it's n minus n minus zeros factorial. Is 10 factorial too big? 10 factorial is not too big. How do you do factorial? Python. This is just select. Factorial. Math.factorial. Okay, yeah. This math.factorial of the number of non-zeros, the number of non-zero spots. Yeah. And then for every for every digit or D in range of 1 through 10 if the digits is in counts, then ways would divide equals math dot factorial of the frequency of that digit. Oh my god. And I think that's it. That's it. Oh, okay, and then I need to add that number of ways to the answer. Self dot answer that number of ways. Okay. So it does all this if you see a palindrome divisible by k. Alright, is it worth it to try to test it now? Probably. Not going to comment all this out. Okay, so there's no backtracking. Alright, let's go ahead and just see if this runs on a very simple case. Let's say n is 2 divisible by 1. So it should be 9 ways. So for every possible that's fine. Place. I think this is the thing already. Okay. So this is all this jazz. All right. Self.backtrack has no attribute. Has no object attribute. Solution has no attribute backtrack. Did I spell things? Self.backtrack is the function. No. Does this work? I don't think this is how you call it. Max place is not defined. Max place is defined. Oh, max places. Digit is not defined. So if D is in count, return the answer. What's going on here? Okay. Let me go ahead and just print out what the combos are that it's getting. Oh, SpaghettiOs. That's way too many ones, twos, sevens, nines for n is 2. Okay, so tracing through this. Starting answer, max places should be 2 plus 1 is 3, divided by 2 is 1. So 1 combos, values, start from 1 through 10, so start is 1, so the first digit is 1, so backtrack of digit 1 where the value is hopefully 11. First call with the value is like 11, 22, 933. Okay. So place is 1, value is 11. This should be matching. 1 is the max places. So this should be if the value mod k, value is divisible by 11 divisible by 1, that's true. And then the digits is going to be a list of character 1, character 1. Third digits is going to be just character 1, character 1. That converts back to 11. And 11 is non-combos. Add 11. Doesn't add 11. Doesn't even add a number, adds a string. Why would add a string here? Huh. So yeah, print out what's going on here. Print out the digits, sorted digits, sort them. Okay, 1, 1, 1. Reduce x, y to become oh, whoops, forgot to do this part. Digits is the integer of d for every d in the string of value. Sweet, sweet Jesus. Okay. Okay, so let's try when n is 4. Not doing the case where it's odd yet. Odd number digits. Really don't know how this should be called. .self.backtrack works. That's the way of calling it. Is it because I'm not including backtrack outside of this method? Alright, well it works for 4 digits. I'm going to remove the print calls. I mean, it's only that's a lot of print calls. And the printing of the combos. And let's see if it crashes on the biggest case. Let's say case of 8. I did case 8. Case 10? Question mark. I mean, it's super slow. It's probably going to time out if I had to actually do it. But it worked. Okay, so now for the middle case, or for handling the middle digit. So if it's the middle digit, then you don't want to have PV1 and PV2, it's just PV1. So what is this? I think it's just going to be this current num deal. If the PV1 equals PV2, then don't do both. Yeah, so if PV1 not equal PV2, then do this. Else, just do current num equals value times PV1. Current value plus PV1 times possibility. If doing middle digit, don't add both PV1 and PV2 to base value. Okay. Let's say 5. Okay, that worked. Alright, let's try some other. Well, let's try 9, I guess. $215 milliseconds. This is going to definitely time out. There's just no way. Let's do test case. K is 2. Right, test case K is, say, 6. Alright, let's go for it. Yeah. Answer. 84 and 9 test cases. Woohoo! N is 1. Oh, you're saying I didn't handle the trivial case? Oh my god. N is 1 case for so. How should this have handled the trivial case? I guess I assumed here that there's at least assume that there's at least 2 digits here. So if N is 1, then it's just going to be 10 divided by, okay, this is trivial case, N equals 1, n plus 1 return 10 or 9 divided by k. So 1 through 9 for 1, 2, 4, 6, 8, 2, 3, 6, 9, 3, 2, 8, 4, 5, this is 5. Okay, I think that's right. I really don't understand why the self.backtrack doesn't work. Wrong answer? No. Okay. Am I just on the extremely slow end of things? What's going on? I guess everything, like the best solutions are 799. I guess I'm like twice as slow. Half as fast, twice as slow. But this might be one where I say fuck it. I spent 3 hours already. I'll be honest and say this is one where I'm surprised I got an answer. But I think it's legit. Okay. Is there a more efficient way to have done this comparison? I think so. I think if I kept an array of digits along with the base value, then I wouldn't have to create a new digits array each time. I could just pass around it. I would still need to sort it, and I still need to do this other hashing stuff to keep track of which digits I've already dealt with. But it would reduce the array usage, this array conversion. Is it worth it for me to try that? So I have a base value. I mess with the digits, I mess with the thing. Alright, so let's say I have a digarray, and it's going to be 0 times the length of, I should be here. So digarray is going to be 0 times the length of n, and in addition to doing this, I can say the digarray of 0 is the start value, and the digarray of the ones is the start value. Alright, so for each spot, if you're not dealing with let's say you're dealing with common case, so you're going to say here the digarray at the index of the place is equal to this possibility, and the digarray at the index of n minus 1 minus place There's also a possibility you don't have to worry about the middle thing for this one because they're going to index to the same spot. And then call backtracking that. Is that right? Is it going to get dirty? I think it's possible that it gets dirty. Like the later calls to backtrack don't correctly clean the initial setup of the values. So for every possibility, it goes through 0 through 100. So it goes through 0. 0 is actually going to reset the value. Then it goes to 9. And then it goes back, tracks. And then when it goes to backtrack, it goes 2. But then it goes to the next one, which is 0. Okay, I don't think it ever really is dirty. Always kind of fully calculates it. So here I can just use the digarray. So the digits I can just say is your digarray. And then I can sort the digits in the digarray. Let's say here let's say sorted digit is equal to the sorted of the digarray. Why is this? Okay. God damn it. Okay. That did not work. Not even close. Not even close. Oh well, the base trivial case worked. So what did I do wrong here? So the value, so the current digarray should have the value. Okay, let me go ahead and just print it. What's going on here? Print value and the dig array. Oh, this is going to print out too many times. This case, say n is 1, k is 2. Oh, this is the base case. This is trivial case, I'm not going to do anything. This case is n is 2, k is 1. Okay, so 11, 1, 1. That's what I expect. Okay, so what went wrong here? So sorted, the value is 11, the digarray is 1, 1. I must have used digits somewhere else here. Oh, fuck me. Sorted. This should be just the digarray. Okay. Let's remove the print. Oh my god, it's a fucking miracle. Okay. Values that can move that. Okay, I think this is fine. I wonder if this is because, why can't I call, when do you call self.method name and when do you call that? Okay, yeah, I think what I need to do is create this method. I think what I want to do is create the method like here. But then I would have to create the max places as I need to create the max places as another instance variable. I'm fine with this. Okay. Is there any other cleanup that I have to do? Not really, I don't think. Do I need value? I do. Okay. Alright. So, summary. So, what went on here? Man, I'm so fucking tired. Okay. So here, what the method, what I use anyways, I'm not sure. Obviously this is best or whatever, but create go through all possible palindromes of the given length n, and I do this in two ways. One, using a keeping track using both an array of digits, and this is called a digarray, and kind of an bookkeeping through recursive parameters, and bookkeeping through recursive parameters is the value parameter within the backtrack call. So for any palindrome, the first and last spots are the same, and similarly for other corresponding indices. Example, first and second digit and tens digit, etc. If the first spot is like the leading digit and last spot is the 1st digit, then yeah, the second last, third and third last. So used a recursive function, recursive backtrack function that iterates, that has an index parameter, initially called to index 1, not leading digit, where function will go through all possible values for that digit, changing it in the corresponding spot, and then cursively calling to the next spot. To the next index. So how did that work? It was working here. So for a backtrack call with a place and value, the base value is like, I don't know if it's four-digit number where n is 4, then the value could be 1001 or 2002 or 3003, because that's the initial start, right? The initial start is those first and last digits are assigned. So here, the backtrack call would be that base value. The place would be like the first non-leading spot, and then it would determine the place value of that spot and the corresponding spot. So for instance, if n is 1000 or n is 4, then PV1 would be 100 spot and PV2 would be 10 spot. It go through all the possible values at those spots. So like it could be 0, 1, 2, 3, all for the hundreds and 10 spots. And then it'll change it for both the digit array and also for the current number. And then the current number is then called as a parameter into the next iteration of backtrack. So here it'd be calling for place is 2, and eventually you only need to worry about half the places. When place reaches past mid point, no more free spots in palindrome to check, and that then determine if current palindrome is divisible by k, and if so, add the number of ways, add the permutations of current digits to answer if not priorly added. So this is the key part. So two key parts to that. Two key parts. One is keep a set of ordered digits of this k palindromic number to use to verify if it's already been seen. And two is to not trivially calculate the number of ways a set of digits can be ordered, not with no leading zero, with no leading zeros. That was brutal. So the first part of that was from your array of digits, you sort the digits, then convert that back into an integer, and then check to see if that integer is already part of the things that you've counted. If it's not, then add that combination, and then count the number of digits that are, count the frequency of each digit within that set. So for instance, if it's a palindrome that is like 1100, 120011. Then so that's not in palindrome. 120021. Then you have 2 1s, 2 2s, 2 zeros. The number of ways to order that such that there's not a 0 in the first spot would be, out of the non-leading spots, choose some number of them for your zeros. So the combinations of n-1 non-leading spots, choose some number for your zeros, and then multiply that by the number of ways you fill in the other spots. The other spots being filled with some symmetric or some duplicate value. So that'd be, in general, that's the factorial of the number of spots divided by the factorial divided by any duplicates factorial, or the frequency of any duplicates factorial. So the number of non-zero spots is n-minus zeros, and then for each frequency of non-zeros, divide by the factorial of that. That gets you your number of ways. You add that number of ways to your you add that number of ways to your answer. Anyways, walk through time complexity. No, there's time complexity for this thing. It's O of the number of ranges. This is weird. Kind of like O of the range of values times O of your, because you're dealing with arrays, where the arrays is the number of digits. Number of digits in your thing. So I think it's times O of the n, where n is well, your range of values is the number of digits. Your range of values is also based on your number of digits, I think. So O of n squared, maybe? Since range of values is based on number of digits. Yeah, you backtrack through all the possible values pretty much. And yeah, space complexity, this should be at most O of n for the arrays, for the digit array. Yeah. Sweet Jesus.